All right, welcome everyone. Happy Thursday, happy November. We are rapidly, I was just in a meeting where I was starting to plan data collection for early 2021 and realized that it's going to be here before we know it. So enjoy the race at the end of the year. A couple of quick announcements and housekeeping. If you organize a symposium for MCLS 2020 and you have not yet presented in the virtual MCLS format, we will be reaching out to you to schedule those symposia for 2021. We will also be sending out various emails trying to get a sense of people's schedules for 2021 so that we might be able to schedule these symposia either during this time, if this continues to work for everyone, or during another time that works better for people. We're also going to make a note to have some other meetings at times that are not convenient just for those in the US and Canada and Western Europe. Noting that Pierina is here at bedtime in Singapore. We want to make sure that we can also reach all of our folks who are on the west coast of the United States and in Asia and Eastern Europe and Australia. So hopefully we'll be able to reach even more people in 2021. And just another note on the US as being the center of the world. I recognize that this isn't a big deal for everyone, but just know that we're thinking about the election and the election results rolling in. It is weighing heavily on me and I know some other people, so make sure that you're taking time for yourself. Feel free to reach out if you need anything. And sometimes don't tell the adults in the room, but sometimes productivity isn't everything. So make sure you're doing what you need to take care of yourself. So with that, I am probably fired as MCLS co-president and will never get a job. But here we are. I'm super excited to introduce our speaker series for today on counting and cardinality, which Matthew Inglis so kindly organized. I will make him co-host as well, just in case he needs anything. So we'll have 3 presentations, and Bert Smedt will be a discussant today, which means you get to hear less from me and more from others. So with that, I'm not sure if you wanted to give any kind of formal introduction or if anyone wanted to get started. I'm not sure if you have an order of presentation, but please join me in welcoming all of our speakers today.
Thank you, Andy. I really appreciate that. Yeah, we have 3 talks. We're going to start with Elisabeth, who's going to tell us about the reliability of the given number task. And then Pierina is going to tell us about CP knowers and whether they understand cardinality or not. And then Theresa is going to finish with a talk about whether highlighting set size facilitates number learning. And because we have a discussant today, we'll be taking 1 or 2 clarification questions only after each talk, and then hopefully leave the substantive discussion until after Bert's discussion at the end. So with that, I'll pass over to Elisabeth.
Yeah, hi. So I'm just going to start sharing my screen. All right. All right, so can you all see my the slide? Awesome. All right, so hi everyone, my name is Elisabeth. I'm a grad student at UCSD, and today I'm going to present a talk, how reliable is the given number task, that I worked on with my collaborator, David Barner. All right, so as many of you know, given number is a task that is frequently used in number cognition to assess children's understanding of number words. So in the task, the experimenter provides the child with a set of counters. So for example, it could be 8 toys cookies, and the task, then the experimenter asks for a specific number of objects. So the experimenter could say, for example, can you put 2 cookies on the plate? And then the experimenter proceeds to other numbers with the goal of identifying the highest number that the child understands, or the child's knower level. Sorry. All right, so using this task, researchers were able to document the sequence or the stages of number words acquisition. So first, children are able to recite the count list, but without actually attaching any meaning to the different number words. And so for this reason, these children are called non-knowers or zero knowers. Then children develop an exact meaning for one, meaning that they're able to give one object for a request of one, but they can't give reliable answers for larger numbers. And still, children at that stage are called one knowers. Then children become two knowers, meaning that they can provide one and two objects on the request, but they won't give reliable answers for larger requests. And following the same pattern, children become three knowers and then four knowers. And after going through these subset knower level stages, children then seem to realize that that the last number word used when counting refers to the cardinality of the set or the total amount of object in the set. And this is why children at that stage are called cardinal principal knower. So a given number is the principal task that has been used to document those knower level stages. And it is also used in correlation with other aspects of development. But the problem is that we don't know how reliable the task is. And this is important when we want to establish those correlations with different aspects of development. And what makes this question perhaps a little bit harder to address in a case of given, so its reliability, is that there's an important amount of variability in how the task is administered across different labs. So in this study, we investigated the impact of two factors on the reliability of given, so namely the version of given used, so either the titrated or non-titrated, which I will explain in the next slide, and the testing environment, so either in lab or out of lab. So what is the difference between the two versions or ways of administering given? So the titrated version is comparable to a staircase administration in the sense that the request for object depends on the child's pattern of response. So if there's a success, so we can imagine, so the experimenter starts at 1, there's a success, then the experimenter asks for the next largest request, so that would be 2. If there's a success, he moves on. And importantly, if there's a failure, then the experimenter goes back to the previous largest request, so here that would be 2. And then this pattern is repeated until the experimenter can satisfy the criteria to assign a knower level. All right, so the non-titrated version is much more straightforward in the sense that the requests are fixed, and based on the child's overall pattern of response, the experimenter can attribute a knower level. So these are the criteria that we use to assign knower level, and they're inspired from Wynn's original criteria. So first, the child needs to succeed at a number n 2 out of 3 times. There's also need to be failure 2 out of 3 times at n+1, and can be used for requests other than n too often. And children are credited as CP knowers if either they follow this pattern or if they succeed on all requests 1 to 6 consecutively. So in this project, we assessed the reliability of given, and we did this to 3 experiments. So in experiment 1, we assessed the test-retest reliability of given titrated. In experiment 2, we assessed the test-retest reliability of given non-titrated. And in both experiments, we asked if there was an effect of testing environment, so either in lab or out of lab. And finally, experiment 3, we assessed both versions of given within children, and we compared the outcomes of these 2 versions to that of another task that is often used to assess also number word understanding, which is what's on this card. So in experiment 1, we tested 81 children, and these children were presented with 3 tasks: given titrated a first time, then a counting task, and then given titrated a second time. And so the graph here displays the knower level obtained in the first assessment. So in the, you can see in the x-axis, and the y-axis is the result of given titrated in the second assessment. And the number in the cell represent the number of children with a certain type of knower level combination. So for example, there were 22 children who were classified as CP knowers in the first assessment and also in the second assessment. Right here. Okay, and so we also use colors to code the density. And what is important to notice is that the density or color is highest on the diagonal. And that is good news because it suggests that there's a high concordance between the knower levels of the 2 assessments. We also use the kappa statistic to assess the reliability, and we obtain a pretty high reliability for the task overall, so 0.87. So, however, as you can tell just by looking at the colors on the diagonal, you can see that there's a lot of variability in the reliability depending on each individual knower level. And so we looked at the reliability for non-knowers and CP knowers separately. And they were both quite high. So this means that children who were classified as a zero knower or a CP knower in the first assessment were likely to receive the same knower level in the second assessment. And this was the case within the group of subset knowers in which the reliability was more nuanced. So it seemed that it was quite high for early subset knowers like 1 and 2 knowers, but much lower for 3 and 4 and 5 knowers. However, when we look at knower level groups, so looking at either zero knowers, binning together all subset knowers and CP knowers, we found that the reliability was higher. So children classified as a subset knower in task 1 were likely to remain subset knowers in task 2. So in experiment 2, we had the same design as in experiment 1, but with a non-titrated version of given. We tested a different group of 81 children, and they were presented with 2 non-titrated given with a counting task in between. And so for the result, again, we obtain a high reliability when all knower levels are considered at once. And again, there was a substantial amount of variation when looking at the reliability of knower level individually, especially within the group of subset knowers. And so the reliability of non-knowers and CP knowers was high. The reliability of knower level group, so again, zero knowers, all subset knowers, and then CP knowers was substantial, but perhaps a little lower compared to the titrated version. So to summarize the result of experiment 1 and 2 so far, these results showed that the titrated and non-titrated versions are highly reliable when we look at all knower level at once and when considering knower level groups. So kids, again, classified as zero knowers, subset knowers, or CP knowers. There was, however, important variability in the reliability across different knower levels. And overall, it looks like the reliability of the non-titrated given was perhaps a slightly bit lower than the titrated version. Also, there was no effect of testing environment. So in order to better understand how the titrated and the non-titrated version compare to each other, in experiment 3, we asked whether they would generate the same knower level within the same child, or perhaps does one version has a bias to generate higher knower level? And so that is the first question that we had asked in experiment 3. Our second question in experiment 3 is, which version should we use as researchers? How can we decide which one provides a more valid output? And to do this, we compare the outcomes of these 2 versions to what's on this card. So in experiment 3, we tested a different group again of 75 children, and they were presented with 4 tasks: given titrated, given non-titrated, a counting task, and what's on this card. So in what's on this card, an experimenter presents a child with a picture containing a certain number of objects and asks how many there are and to count them. And then the experimenter can assign a knower level again based on the same criteria as given. So we first look at the result of given titrated versus non-titrated. How reliable are their output? And so we obtain a kappa of 0.71, which is relatively high, but still lower than the 2 versions individually. So lower than the result of experiment 1 and 2. And so when we look at knower level individually, we found that the CP knowers and the 1 knowers were quite reliable, but that was not necessarily the case for other knower levels, especially within the group of subset knowers and when looking at knower level groups. So this suggests that there's some amount of difference between the knower level obtained in the titrated and non-titrated given. And so if we take a closer look now, we see that there were 45 matches and 30 no matches. And if we look at the graph here, it plots a distribution of differences in knower level across the task in the x-axis. And here, positive number means that the titrated knower level was higher than the non-titrated knower level. And negative number means the reverse, so that the knower level obtained in the non-titrated version was higher. And so what is interesting here is that the majority of no matches differed by only 1 knower level. And this difference tended to be in favor of the titrated version. So this means that the no matches were composed mostly of children who were classified as having, in the titrated version, 1 knower level above that of the non-titrated version. All right, so even if the 2 versions of given had a reasonably high reliability, the titrated version still generated slightly higher knower levels. So the next question is, which version is more valid? How do these results compare to what's on this card? So it turns out that this question is actually a little bit tricky to answer. So when comparing what's on this card and the titrated version, we observed that there were 33 matches and 42 no matches. And when comparing what's on this card and the non-titrated version, we found 37 matches and 38 no matches. And so when we look at the distribution of differences between titrated and what's on this card in the graph here, we found that what's on this card generated higher NOE level, and not just interestingly by 1 level, but also by 2 and 3 levels as well. In a similar kind of pattern of result, when we look at the difference between the non-titrated given and what's on this card, what's on this card generated higher NOE levels, and the distribution of the differences is quite spread out. All right, so to conclude, in experiment 1 and 2, it shows that both given versions individually have a high reliability, but that is somewhat nuanced depending on individual NOE levels. And so this suggests that using either all NOE levels together or NOE level groups, again, so zero NOERs, subset NOERs, and CP NOER as predictor is perhaps the more cautious way of assuring reliability than using any individual NOE level stage. Also, there was no effect of testing environment. In experiment 3, we found that the titrated and non-titrated given generated somewhat similar NOE levels, but perhaps the titrated version generated slightly higher NOE levels. However, when we compare these results to what's on this card, we found that the NOE levels of both givens seem to differ from what's on this card. In fact, it seemed that what's on this card generated consistently higher NOE levels, and not simply by a difference of 1 level, but 2, 3, and sometimes 4. So even if the titrated version generated slightly higher NOE levels than the non-titrated version, that difference was smaller than the difference between what's on this card and the 2 given versions. So in terms of which version should we use as researchers, so which version of given should we use as researchers? Well, given that they generated somewhat similar outcomes, it could make more sense to use the titrated version, as it is also faster to administer and therefore more appropriate for younger children. All right, so I'm out of time, so I would like to finally thank the MCL Society for this opportunity to present my work, the members of my lab for their support and input, as well as our funding agency. Thank you.
Lovely, thank you, Elisabeth. So whilst Pierina is getting ready, if anyone has a quick clarification question, perhaps you could put that in the chat. Otherwise, we can move straight on and leave the substantive discussion until after Bert's discussion session. So I'll give it a few seconds to see if anyone has a clarification question. It was a very clear presentation, so maybe not. Okay, well, let's move on to Pierina's talk then.
So is there anything I should be doing right now?
There's a question from Andy in the chat. Maybe we can just take that before. Can you see that, Elisabeth?
No, I can't for some reason. Oh, I see. Let me just.
Okay, I can read it out.
I'm so sorry. All right.
So Andy asked when this is going to be published.
Oh, hopefully very soon. So I'm still working on the discussion right now.
Great, thank you. Great.
Fantastic. So if Pierina's ready, we shall move straight over to her.
All right, so I'll get started. So I'll present a couple studies on children's acquisition of counting, focusing on CP NOERs. And this is work done with Anders Schusterman at Wesleyan University. So to learn counting, following Gammon and Gallistill's counting principles framework, children have to acquire 3 how to count principles. The first one is the stable order principle. Children have to follow a fixed order of number of words every time they count. And then the second principle is what we call the word-object correspondence principle, or what they call the one-to-one correspondence principle. Basically, every time you count, you're applying just one number word for each object. And finally, the most important principle of the 3 is the cardinal principle, which Elisabeth has talked a little bit about. So the cardinal principle basically means that if children understand counting, they should understand that the last word of a count tells you how many things there are in a counted set. And typically, there are a couple different ways to assess cardinality or the cardinal principle. One method is the how many task. So on this task, you give kids a bunch of objects, you ask them how many, and then you test whether kids would respond with the last word of a count in response to a how many question. Well, one issue with this task is that children could simply respond with the last word without actually understanding the meaning of it. So over the last few decades, researchers have been using the give-and task, which again, Elisabeth has talked quite a bit about, to assess students' understanding of number words and also cardinality. So on this task, students give the experimenter or puppet a certain number of objects, and we use this task to classify children into different neural levels. And the very last stage of number word learning, according to this task, is what we call the CP stage, where children are able to give numbers past 4, so they can reliably give 5 or 6, and sometimes up to 8. And CP knowers are thought to be the kids who know cardinality. But testing cardinality using the given task only really provides part of the picture. And the reason for that is that the given task primarily tests whether kids can give n when you ask for n. But if you really think about it, understanding cardinality means that you understanding the last word of a count tells you how many things there are in a counted set, if and only if you're following the stable order principle and the word-object correspondence principle. And what this means is that children should not just understand that last word tells you cardinality when I'm counting correctly, but they should also understand that the last word doesn't tell you cardinality when so the last word doesn't tell you cardinality when you're violating the counting procedures. And this is what we're testing here. So in this study, we asked whether children understand the second piece of the puzzle to cardinality. We use the error detection paradigm. So in this paradigm, there are 2 characters. One is the experimenter, the other is the puppet. The experimenter asked for n objects, and the puppet would count out n objects, but on some trials, the puppet would violate the counting procedures. But nevertheless, the last word would still end on n as per the experimenter's request. And then we asked kids, are there n objects? And we used the given task and only included CP knowers in this study. So just to give you a quick demo of this paradigm, so here's the experimenter asking for 5 fish. Can you put 5 fish in the bucket? And there's little hippo, and hippo said, okay, let me help you. And hippo will then proceed to put in 4 fish, but counted 1, 2, 3, 5. And the last word ended on 5. And then we asked, are there 5 fish in the bucket? Again, like I said before, if children understand that the last word doesn't tell you cardinality when you're violating the counting procedures, they should answer no. There are not 5 fish in the bucket. So we have different trials. Some trials, everything is correct. There's no counting error. The last word matches the experimenter's request. On some other critical trials, the puppet is making a mistake, just like what I showed you with hippo, but the last word matches with the experimenter's request. And we also have trials where the last word doesn't match, but there's no counting error. So if children understand the last word tells you cardinality when you're counting correctly, then when everything is correct, they should say yes, there are n fish in the bucket. But if they also understand it, and if they also understand that the last word doesn't tell you cardinality when the puppet is violating one of the 2 counting procedures, then they should say no on some of the trials where the puppet is making a mistake, but the last word matches. And they should obviously also say no when the last word just doesn't match, even if there's no counting errors. So we have 4 different trial types and 2 set sizes. So we have small sets and large sets. So we tested 42 kids. They're all CP knowers between 3 and 5. And remember, again, the question is, are there N fish in the bucket? So here, y-axis is proportion of yes. This is kind of the ideal case. If they understand the 2 pieces of the puzzle to cardinality, then they should say yes only when everything is matched. So when the last word matches and when there's no counting error. But when there's the violation of the counting procedures, or when the last word doesn't match, then they shouldn't say yes. And this is what we found on the small trials, on the small sets. Interestingly, children have a last word bias on the large sets. So even when, on the large sets, even when the puppet is making a counting error, when the last word matches, they say yes, there are N fish in the bucket. So what's going on here? One explanation may be that children just didn't see the errors. Maybe the large sets were just more taxing because it requires higher attentional load. So to test this explanation, we ran a second study where we used the same exact paradigm with the hippo, with the fish, with the bucket. But instead of asking whether there are N fish in the bucket, we asked kids whether they agree that the puppet have done a good job or whether she messed up. So, so this is what we found. So we found that actually kids are quite good at recognizing the errors, but only for the stable order errors. They're not very good when the error is a word-object correspondence error. So again, this is quite surprising and interesting, and we're still trying to figure this out, but there are a couple kind of different explanations that we're entertaining here. So one potential reason, it seems that maybe one possibility is that children did detect the error, but they're somehow more tolerant of it. So if this is the case, it would suggest that maybe not all counting errors are equal, and maybe children have some graded knowledge of the counting principles. One interesting observation is that this finding is actually consistent with their own counting behavior. So in this task, they're reasoning about a puppet's counting behavior. But in some other studies, we also see that CP knowers actually also make word-object correspondence errors, especially when sets are larger than 10. That said, it's not really the full kind of explanation because children's performance on a small set wasn't that great still compared to the stable order errors. So to summarize, we found a lost word bias in the first study, and we were trying to figure out whether it was because CP knowers didn't notice the error, and that's why we ran study 2. Given studies 2 results, the answer is that this last word, this explanation that children didn't see the error might not be the full story, because children in study 2, children can actually detect stable order errors, and yet they still showed a pretty strong lost word bias on these stable order trials in study 1. So what we're going to do next is that we are testing potentially another alternative explanation, which is that maybe kids just have a very difficult time to say no when the last word matches. We have control trials to rule out yes and no bias kids, but just to be really sure that it's not something with response bias or inhibition, we're planning a follow-up study where we also provide the correct number of fish in the question. And we also plan to run this within subjects. So in what I just presented is a between subjects design. So different kids participated in study 1 and study 2. In a follow-up study, we plan to run this within subjects. So what are the implications of this study for the acquisition of cardinality? It seems like it when children become CP knowers on the given task, it doesn't actually mean that they have acquired or fully acquired the conceptual knowledge that underlies the cardinal principle. And what we're arguing is that to understand cardinality, children also have to understand when the last word doesn't apply. So thanks for all the wonderful RAs at Wesleyan for collecting data and for our funding agency for this, for supporting this.
Fantastic. Thank you very much. So again, if anyone has any quick clarification questions, please either jump in verbally or post a quick comment in the chat while Theresa's getting ready for her talk. Okay, let's jump straight ahead then to maximize our discussion time. Theresa, are you ready to get going? So Theresa, we can't hear you, but I can see your calendar at the moment.
Sorry, let me try that again. Okay, share screen. All right, is that working?
Yeah,
Do you see?
That's
and
fine.
you see the presentation in the big mode?
Correct.
Awesome. Sorry, I don't know why that was so difficult. I practiced. Yeah, thank you. I'm Theresa. I'm a PhD student at the Center for Mathematical Cognition at Loughborough University. And together with Rebecca Merkley, Pierina, and Daniel Sari, I investigated whether highlighting set size when teaching numbers to young children could facilitate their number learning. So in the previous presentations, we already heard about children's stepwise acquisition of the first small numbers before they understand the cardinal principle of counting. In this study, we focused on children who are subset knowers to look at whether we could facilitate their learning of the next number. So 2 knowers becoming 3 knowers, 3 knowers becoming 4 knowers. Learning the first small numbers is a very slow and effortful process for children. One reason why it's so difficult for subset knowers to learn the next number is that they have to figure out that the number word refers to exact set size, regardless of any other properties of the set. For example, where the number word 3 applies to 3 dogs, a different set of 3 dogs, but also 3 sheep. All these sets are 3. Once a child has learned that the first card of dogs shows 3, so they know this is 3, do they also understand the meaning of the number 3? And in order to really understand the meaning of the number 3, a child has to understand that the 3-ness of a set of dogs has nothing to do with the dogs, but only refers to set size. And sets of different things other than dogs can also be 3. Cheung and colleagues show that subset knowers could learn the next number from a training that showed examples of sets. Here, 3 dogs, and some sets that don't have 3 dogs. However, the children who learned about 3-ness from this training with 3 dogs seem to only be able to correctly identify sets of 3 dogs, and seem to be guessing when they were asked whether a card showed 3 sheep. And by the way, these are not the original stimuli used in the study, but just pictures I used for illustrative purposes. It seems like subset knowers can learn the meaning of the next number. And the set size it refers to from exposure with clearly labeled examples, like here cards with 3 dogs. But what they seem to struggle with is generalizing their knowledge of set size to sets of different objects. So making the step that the 3-ness has nothing to do with the dogs, but it can be applied to any kind of set. And this leads to the aim of our study. We wanted to see whether we could facilitate subset knowers learning of the connection between number word and set size, regardless of the objects in a set, by highlighting in a brief exposure training that sets of different objects can both be correctly labeled with the number word. Here's a short example of how this training looked like and how we tried to highlight set size in the sets for the number 3. So we would show this on an iPad to the children, and the experimenter would always describe what's on the screen. So here, look, hearts, there are 3. Look, clouds, there are also 3. Look, hearts, there are not 3. Oh, sorry. Let's quickly go back to where we see all of them. So we would show a set with the next number that the child had to learn, then another set that also had that same set size, but had different objects. And finally, we would show a set that had the original objects again, but this time does not show the number that the child is supposed to learn. I'll show you a few more examples while I keep talking. So the idea here is that this brief exposure training could highlight that the number word refers to set size by showing that sets of very different objects, like stars and flowers, can both be 3, while sets of the same objects don't necessarily have to be 3. So the 3-ness has nothing to do with the objects in the set. To evaluate whether this training actually highlighted set size and facilitated number learning, we recruited subset knowers to train on the next number that they had to learn and compared this new experimental training to a control training. We used an initial given number task to select children who were subset knowers and could be trained on the next number. We then assigned these children randomly to one of the 2 training conditions. In the experimental training, we used the trials like the one I just showed you, and children who received the control training would only see sets of the same objects in each trial. So only stars, only flowers, only hearts, etc. Idea here was that the control training would lack the contrast of sets of different objects, but the same set size that we use to highlight set size as the relevant property in our experimental training. All children would see 8 training trials like this before we tested their knowledge of the trained number. We did this by using a 2 alternative forced choice task where children had to pick from 2 sets, the one that showed the number they were trained on. So look, stars, which one has 3? And this was again presented on an iPad where the children could just show us which of the sets they think had 3 objects. The sets we showed in the 2 alternative forced choice task included sets with objects that children had seen in the training, as well as novel objects, like these bow ties here. We also varied the ratio between the 2 choices. Children completed 8 trials of the 2 alternative forced choice task, and then completed another given number task at the end of this experiment. We included 65 Canadian preschoolers in this study, but we tested a total of 149 children with the given number task. just to find 2 and 3 knowers that could be trained on the next number. We pre-registered the study on the OSF, but given how difficult recruitment for the study had been, we had to make some post-hoc adjustments to our plans for sample size and inclusion criteria. I can say more about that later if you're interested. We still conducted our pre-registered comparison of accuracy on the 2 alternative first choice task between children who received the control training and children who received the experimental training. We used this comparison and a pre-registered one-tailed t-test to answer our main research question. Do contrasting sets highlight set size and facilitate number learning? If so, we should see higher accuracy on the 2 alternative first choice task for the children who received our experimental training. And indeed, we found that children who received the experimental training that highlighted set size performed significantly better than children who received the control training. However, many children in both training conditions did not perform above chance. And this might have to do with what I told you earlier about our adjustment of the inclusion criteria. So for now, if I have some time left, I'd like to show you the results of 2 further exploratory analyses. But I think we're out of time. Matthew?
If you're quick, you've only taken 9 minutes, so if you're quick, you can certainly do that.
All right. I'll try to be super quick. So we also looked at whether learning the next number with the contrasting sets would facilitate children's generalization of this knowledge to novel sets, so the sets that the children hadn't seen during the training. Findings here are inconclusive, but there seemed to be some indication that the children who received the experimental training performed better than children who received the control training, even for novel sets. And we can see this especially when comparing the number of children who were perfectly accurate at picking out the trained number. You can see in the yellow dots up here, most of these children received the experimental training. And lastly, we also compared performance on the given number task and knower level classification from before the training to afterwards. This would also allow us to see whether children might have been able to generalize the knowledge of the next number that they acquired from our training. We found that quite a few children were classified in a more advanced knower level after the training. So some 2 knowers now becoming 3 knowers, 3 knowers possibly being 4 knowers. We already heard in the previous talk that the classification from the give-n task is not 100% accurate. It might vary just regardless of learning about numbers. However, there seemed to be an interesting trend that children who received the experimental training were also more frequently classified as having advanced knower levels compared to prior to the training. So to conclude, we designed a training study for subset knowers and asked whether contrasting sets could highlight set size and facilitate children's number learning. According to our pre-registered and exploratory analyses, my answer to this question is yes, maybe. So I think these results are quite promising and very interesting, but we're planning on some follow-up studies to look at the role of contrasting sets for number learning in more detail. Thank you very much.
Fantastic. Thank you very much, Theresa. So again, whilst Bert's getting ready for his discussion, if anyone has a very quick
I have a question.
Please go ahead.
First of all, thank you very much. It was very interesting. I may be getting carried away with my question, but can it be that the fact that sets that are over 3 is simply, you simply say that they're just not 3? In other words, looking forward and learning how to count, if someone has 4 toys and someone asks him for 2 toys and he'll say, I do not have. Did you think of this?
Sorry, I'm not sure I understand the question.
In other words, you're teaching them that sets that aren't 3 are simply not 3, not that they're bigger than 3 or smaller than 3. Could it maybe cause problems further on? For example, if they have 4 toys and someone asks them, do you have 2 toys to give me? And then he says, no, I have 4 toys. In other words, they don't know the concept that they have less or more.
Yeah. So I think I wouldn't be too worried about that, because I think our results show that children learn like very little from these trainings. It's a very brief training. So I don't think we're like messing up their numerical development with showing them these examples without clearly labeling them. I think for us, it was important to like really stick to the concept of threeness. So not confuse children with saying, well, now it's 4, it's more than 3, but like really just having some examples for 3 and some examples for not 3 to highlight what it is that they have in common or not in common, if that makes sense.
Yeah, so I was being carried away. Thank you.
Thank you very much for that question. So let's move straight to our discussant, who very kindly agreed to talk about the 3 presentations. Over to you, Bert.
Oh, thank you, Matthew. Thank you for organizing this symposium and for inviting me as a discussant. I think the topic of the symposium is extremely timely. Who could have thought that the issue or the act of counting would be a major political issue today? I also would like to commend the presenters. I think they had very nice visuals on their presentations. I think this is a good thing for the audience. It makes the job of a discussant slightly harder because one does not always know what some types of visuals would represent. I will go quickly through the 3 presentations, do a brief summary and highlight some questions or ideas that I had, and hope I have a lot of time for discussion at the end. So the first talk by Elisabeth was about a prototypic task that has been used to investigate children's counting, and it's the given number task. And the key question that was addressed was the reliability of the task. And to answer that question, Elisabeth compared titrated and non-titrated versions of the task with each other and looked at the reliability of these different variants. And the key finding was that those versions were reliable. They were particularly reliable to determine CP knowers. They were slightly less reliable for determining subset knowers. And there was a slight advantage of the titrated versus the non-titrated version of the task. And I think this is also happening because of the specific design of the titrated task, because it uses a stepwise procedure. And by this design, it actually reduces measurement error because it avoids errors that may be related to fatigue or to a lack of attention throughout the task, which may be more problematic in the non-titrated version. And so this type of design is also very common in other tasks, like, for example, memory tasks, where you have these span tasks that work also in the same way. And it resembles to the model of high jumping. And I have put a picture that perhaps nobody will recognize, but there was one time in the history of high jumping in 2008 where Belgium won a gold medal on the women's competition. And this high jump model brings me to my first type of or first outstanding question, which is about the underlying psychometric model that is behind this given number task. And I think this is an interesting question to think about, as there could be different types of model behind this task. And one model could be that we have a kind of an ordinal scale, like in a Goodman model and like in the high jump competition, where you have different types of stages and you go from one stage to the other. Another way or another possibility would be that this is not just an ordinal model, but more of a stochastic model, like in an item response theory model. So it might be an interesting idea to look from a psychometric point of view to the task to determine the kind of model that is behind it. And other point is related to, and it was also raised in Elisabeth's presentation, is related to the validity of the task. I mean, there was one test of validity in the presentation where Elisabeth looked at the overlap or the correlation between those given number tasks and what's on the card task, but there might be other ways to look at validity. Empirical ways, like correlations with other types of tasks that are trying to assess counting, but also on a theoretical level, there's probably it would be interesting to look at the question of validity and to understand whether the given number task is really measuring the understanding of counting. And this brings me to the second presentation by Pierina, which was about the validity of the given number task. And the idea was that the understanding of counting not only requires an understanding of cardinality, but also of the principle of stable order and the principle of word-object or one-to-one correspondence. And Pierina investigated this by means of an error detection paradigm, where CP knowers were asked to see if there was an error in the counting of the puppet. And she actually revealed that CP knowers, as determined on the given number task, may not fully understand all the other principles related to the understanding of counting. And particularly the word-object correspondence principle seems to be difficult to understand. And this was especially true when large sets were administered. Some doubts here is that clearly there seems to be different types of CP knowers, and it would be interesting to investigate to which extent those who make these errors in the word-object correspondence principle differ from those children who do not. Another thing to examine is the origin of these errors, and it was already hinted in Pierina's presentations. This could be related to working memory. It could also, given that it particularly occurred in the large sets, it could also be due to the understanding or the use of large number words. And another thing that I think might be interesting to look at is the use of more complex counting strategies, like counting in by twos or by threes, where the one-to-one correspondence principle is has a slightly different meaning. Then the last presentation by Theresa was focused on a particular category of children, namely the subset knowers. And she investigated the extent to which they understand that number is an abstract property that refers to the set size. And she administered she gave children a training to learn this. And this was done by contrasting two conditions: a control condition where children or there was a match between the set size and the object which the set had to be determined, and then the experimental condition where there was not a match between the object and the different sets. And she found that her training had a small effect. And things that I wondered were about this training was really with concrete objects, but I was wondering with abstract objects, but I was wondering to which extent this would generalize if more concrete things like animals, like cookies, I'd be more motivated when it comes to cookies, were used in this kind of training. Also, the training was quite passive, so children simply had to watch, and one might wonder to which extent the results would change if the training would be more active, if the children would be really doing the act of counting with materials. And a final interesting thing, and Theresa alluded already to it, is that the criteria for inclusion that were pre-registered were not met for a lot of the children. And one outstanding question for me at least is to which extent or how one should deal with those kind of issues. So to conclude, I would like to highlight a few challenges. One is that, at least from these presentations, we need a better understanding of subset knowers, and one possibility might be to do some microgenetic work very carefully to see how children transition from one to the other type of subset knower. We also saw that this category of CP knowers might be heterogeneous, and that there might be distinct categories within this group. And so it might be interesting to do some kind of latent profile analysis on this group to see what type of trajectories are emerging there. there's a need for a better understanding of the measurement of counting, and perhaps not only one task, but a variety of tasks should be used to see whether children really understand the different principles of counting, and that hopefully will lead to better ways of fostering the understanding of counting and cardinality, not only in the preschool environment, but also in the home environment, and suggestions to optimally do so might be delivered to parents. And with this, I would like to thank you for your attention.
Fantastic. Thank you very much, Bert. I'm afraid I failed in my chairing duties, so we don't have very long for questions. But if I could invite, firstly, any of the speakers to respond to any of Bert's comments, if they have thoughts, whilst other people are alerting us to the fact they would like to ask a question in the chat.
Respond to the things you brought up about our study, and especially about like what do we do to deal with the pre-registration meeting the reality of testing 3-year-old children, because we had really long discussions about this. And what we decided to do is now in the paper to report both, consistently report this is what the data looks like with the inclusion criterion as pre-registered, which is only on like a third of the children really that had done the task, and then report the results with the whole set of children who completed the study, but maybe didn't pay as much attention as we would have liked them to. Which like leads to the other thing you mentioned about our training, and that it was really boring, and that it would have been a good idea to engage children more actively. We tried, there was like a little finger puppet presenting the training. It was on an iPad, but yeah, I think it's a really good idea to make it more engaging, use maybe manipulatives instead of just pictures to really focus children's attention.
Theresa, can I ask a follow-up question? So if those two analyses end up with different interpretations, you still have to decide which interpretation to focus on in your discussion. So, you know, is that
luckily
actually...
they didn't.
What would you have done if they did, though? I mean, that doesn't really get around the problem, does it?
Yeah, so what happened is nothing was significant if we just looked at the children who met the inclusion criteria, because we only had 24 children, I think, who met the inclusion criteria. So that was like 12-ish in each group. But the effect was in the same direction and even stronger, just looking at the difference between average accuracy. What we would have done if it was different, I guess it really depends on different in what direction. I think we would probably do the same as we do now, which is report it transparently and be like very careful about the conclusions that we draw from it. I think like even with the results as they are, we don't want to like claim that we figured out how to teach children the next number, but just that this might be an interesting thing to look at. But yeah, the training needs improvement, and there might be better approaches to look at it as well.
Okay, I think we've probably gone over our hour, so I should thank all of our presenters, and especially to Bert for a wonderful discussion, and hand you back over to Andy. Pennsylvania, so that has
Thank you all so much. It was a fantastic session and really good timing, so really impressed on that. And we will see everyone next Friday for our next symposium. Hope everyone has a fantastic day and can't wait to see all of these papers in press.
Thanks very much, Andy.
Thank you.
Thank you.